When you study your amino acids, you would often encounter a table like this summarizing some conventions and properties of your amino acids. Let's take a look first at the abbreviation or symbols for our amino acids. So these were created for convenience whenever we want to try to present the sequence of a protein, the amino acid sequence of a protein or peptide, for example. So instead of writing the long names or the complete names of your amino acids to present the sequence of a protein, we can choose to use the abbreviation or the shorter one, which is a one letter symbol. So it's very advantageous or convenient if you memorize this abbreviation and symbol for amino acids. Another thing that I want to highlight here is the pK values of our amino acids. So notice that we have a maximum of 3 pK values. We have the pK1, which is the dissociation of the proton from the carboxylic acid functional group. We have pK2, which is the dissociation of the proton from the amino group. And we have pKr, which is the dissociation of a proton, if there is, from the side chain. So an example, let's take an example here such as tyrosine. So tyrosine is an aromatic amino acid. So let's start by drawing what we call the fully protonated form of the amino acid. It means all of the ionizable protons are still in the molecule. So we have CH2 and then the aromatic ring and then OH. So for tyrosine, we have pK1, which is 2.20, which means at pH 2.20, in a system composed of tyrosine molecules, half of the tyrosine molecules have this structure, while half of them have the proton from the carboxylic acid functional group dissociated. So you have an O negative here. So again, at pH 2.2, we have an equal amount of these two molecules in the system. Next, if we look at the pK2, so we have 9.11, and this pK2 refers to the dissociation of the proton from the amino group. So if we reach a pH value of 9.11, it means that half of the molecules in our system will have this structure, and the other half will have this structure. So the proton is now removed from the amino group. And finally, we have the pKr, which refers to the dissociation of the proton from the side chain. So which proton will dissociate? It's the proton from the alcohol group. So the pK for this is 10.07, which means if we reach a pH equal to 10.07, half of the molecules in our system will have this structure, while the other half will have a deprotonated side chain. So instead of an OH group, what we see is just O minus. So this is how you interpret your pK values for amino acids. So for example, we start with a solution of tyrosine that is at pH 1. If we slowly add base so that the pH increases, of course, some of the protons from this molecule will be neutralized. And if we reach a pH equal to 2.2, then half of the molecules will now be deprotonated at the carboxylic acid functional group. The half still has this structure. As we continue to add base, so the pH is increasing, then more of this is converted to this until we reach an equivalence point. So at that equivalence point, all of these molecules are converted into this. So if we continue to add more base, so some of this will be deprotonated at the amino functional group. So it will be converted into this. If we reach pH equal to 9.11, half of the molecules are converted into this structure and the other half are still like this. Again, we continue to add base. So more of these will be converted into this until we reach a second equivalence point. At the second equivalence point, all of these are converted into this form of the molecule. Again, we continue to add more base. So this one will now be neutralized at the side chain. So the proton from the side chain, the alcohol functional group, is removed due to the neutralization reaction. And if we reach a pH equal to 10.07, half of the molecules would have been converted into this form, and the other half are still in this form until we reach the equivalence point. So at the equivalence point, all of these molecules are converted into this form of the tyrosine molecule.